So have you ever wondered about protecting your customer data privacy when you hold large AI data systems? What if your insights generated by AI or the data which you post on cloud gets leaked? What if those things can lead to re-identification of their data? And that's where data privacy engineering comes in. Hi, my name is Lalit Pant, and I'm from CBA Data Analytics R&D team, and I've got my colleague Ashika with me. And today we are going to talk about some techniques around data privacy engineering and how can those techniques be used to essentially enable responsible AI, especially in the context of sharing data within an organization and outside. So let's get started. First, a quick introduction to my team. As I said, we are part of Data Analytics R&D in CBA, and our main focus is to look at different emerging technology within the data and analytics space, specifically where banking domain comes in. One of our key focus areas at the moment is kind of building a cloud data exchange ecosystem with our partners, where we can share data with partners in a safe, sound, and secure manner. And then when we talk about data sharing, we also talk about multi-party computation, how we can essentially create an ecosystem where different partners can come in and share data and build applications, examples like doing privacy-preserving machine learning or making use of data while keeping it encrypted, as we call it, encryption in use, right? And another offshoot of that particular area is entity matching, how we can match entities across different partners in an anonymous manner, right? And not just limited to customers, but also products, accounts, right? And within the organization, that can lead to identifying duplicates, right? So there are a lot of duplicates, data sets within an organization itself. So deduplication is another problem we are looking at. Because it is related to customer data sharing, data privacy comes into picture, right? How do we protect direct identifiers of customers, like emails, phone numbers? And not just that, indirect identifiers, right? Your age, your income, right? Those which could be joined with other data sets to identify you, right? So we're looking at some of those techniques, and maybe we'll go through a bit more details, in the other parts of the session. Then synthetic data generation, right? Something around how we can use production data to generate some synthetic data which has similar statistical properties, and something which can be used for application development, right? So protecting real production data to be used for application development, and also for model building, right? How we can protect data as much as we can without getting it exposed to the engineers who can still work and build applications where the analytical properties are required. And lastly, but most importantly, we are also looking to build a collaborative analytics ecosystem whereby we are not sharing data with partners, but we are sharing data applications, insights, right? So you must have heard about Streamlit on Snowflake. So that's essentially one enabler to obfuscate your data, but still be able to share the insights. So yeah, if you're excited by any of these technologies, feel free to get in touch with us, and we can discuss more what we are doing. So getting to the topic of today, data privacy, right? So let's start with looking at the two W's of data privacy. First of all, what is privacy, right? So as a definition, it's an ability of an individual to control how their personal information is getting used. And organizations today are trying to solve it by introducing privacy policy, putting up privacy statements on their website, or bringing user consent before using their data for any of their analytical purposes. But on top of that, there are certain engineering techniques that enable it rather than the processes which I just talked about. And those are the engineering techniques that we'll focus on today. Moving on, why do we really need privacy? So first of all, it's the right of each individual that their personal information is protected, right? Everyone wants to defend their personal information. We don't want our information to be exposed. And at the same time, this could be a huge physical risk, physical hazard as well, right? Imagine if a stranger gets to know when you are going to work, when you're going to pick up your kids, or when you're going to, get groceries, right? This could be a huge safety hazard, and that's why protecting this information is important. We are customers of different large organizations, right? We share information, and there's a trust that we build with these organizations that the data will be shared. So if any such information gets leaked, that trust is damaged as well. So it's also about reputation with your customers. We've had, over the last 5-6 years, a lot of regulations have come in to control the way data is shared. Europe has got GDPR. In US, there are 50-odd states with their 50-odd definitions of privacy. And then even in Australia, we've got a privacy law which mandates organization to secure customer privacy. So with these regulations coming in, it makes privacy quite prevalent and quite important. And lastly, but most importantly, we are moving our workloads into cloud as we expand the ecosystem, and with that, the possibilities of data leaks also increase. So we need to make sure that before data gets moved to cloud, it's protected and it's secured, and hence, with the changing landscape, privacy is taking a very important role in our organizations. So let's look at an example, right? How can re-identification attack happen, right? So if you see here, there's this gentleman on the left, and he lands at a Rolex store. He uses his credit card to buy a really expensive and luxurious watch, and he's very excited about his purchase, and he ends up posting this on Facebook, right? And guess what? He gets 5,000 likes, right? So he becomes, he's very happy what has happened. So what do you guys think can go wrong here, right? Well, the bank with which this person is holding the credit card now wants to provide better services to its customers, right? They want to use their rich customer transactions data to essentially predict better services for the customers, and hence let's assume that the bank decides to de-identify the data, take away the personal information, and push the data to cloud to leverage the enormous cloud capabilities, right, to run massive scale analytics. At the same time, because the data is posted on cloud, let's assume the data gets leaked, there are some security vulnerabilities there, but as an organization, we are comfortable that we have done data de-identification, there are no personal information that's getting lost, right? But the individual has also posted the data on Facebook, right? So the attacker that you can see here can actually get access to this public data and then join it with the de-identified data to actually re-identify the individuals. And hence, that essentially leaks out all the historical transaction as well, if such a re-identification can happen. So as we see, we had de-identified data, but then by joining that with certain public data, the information about the individuals can be re-identified, right? And this public data doesn't have to come from the same person through their Facebook account or Twitter feeds. It could come from a general publicly available information. For example, government publishing stats about a suburb, what's the age demographics of a suburb, So if there's a suburb which is, let's say, very sparsely populated, and there are only few people above the age of, let's say, 85, then with just brute force or some intelligent guessing, you can kind of figure out who are those individuals, right? So there's always a possibility of re-identification when we just try to treat or remove some of these personal information. And hence, we need to look at some more advanced techniques on how we can essentially safeguard the data sets. So privacy versus security, right? So there are two terms which are used a lot interchangeably. So I think it's important before we go ahead to understand what is the difference between the two, right? So when we talk about data security, we are looking to control the access of the data. We are looking to ensure that only the right people have access to the right amount of data, right? That's essentially around security. Where privacy comes in is where we are looking to use the data which you have access to in a responsible way, so as to make sure that your personal information is secure. So these are, I think, the key factor where privacy builds on top of security. So security is essentially an enabler for privacy, but just with data security, we cannot ensure that privacy is maintained for the data set. There has to be some specific privacy techniques to enable on top of data security. And lastly, to the last important term for introduction, responsible AI, right? It's a heavy term, but really what does it mean, right? So essentially when we are building an AI system, we need to make sure that we are handling PI carefully. We are making use of PI only where necessary and also in a very safe form. The idea is to keep the systems transparent and fair so that any insights that are generated, they are not biased towards or against a particular race, ethnicity, or gender. So those kind of things are taken care of. At the same time, the system needs to be accountable as well as interpretable about what insights that it is generating. So yeah, with great powers comes great responsibility. So when you are dealing with data, it needs to be handled in an ethical manner, and also the responsibility around different regulations. Like as we heard about a question earlier about regulating AI or data science. So these regulations are coming up day in, day out in different geographies. So it's important to cater to that as well when building AI systems. And lastly, I've mentioned a couple of key domains there, business domains, which should be more conscious about responsible AI, specifically financial services and healthcare, because these are the domains which collect, store, and massage a lot of data sets and use it for the benefit of their customers, and hence the responsibility is higher to kind of secure the data as best as we can. So with this background, what we kind of realized is that privacy and responsible AI are very closely related, right? And they need to go hand in hand. I'll now pass on to Ashika, where she'll talk about some key techniques of privacy engineering.
So in order to power responsible enterprise AI, engineers must balance business innovation with privacy needs. There's a wide range of data engineering, privacy engineering techniques that are available out there, but the four main pillars which we'll be deep diving into in this talk are data clean rooms, homomorphic encryption, differential privacy, and AI fairness and bias. First, let's take a look into clean rooms. I'm quite new to the data engineering space, so when my team started talking about clean rooms, this is the first thing that came into my mind. Just to get a gauge from the audience, how many people have either heard of or worked with clean rooms before? Okay, fair few. But in a privacy engineering context, data clean rooms are abstract spaces where interested parties can share data with each other without violating user privacy. Companies that want to use data clean rooms can provide aggregated and anonymized data sets as opposed to individual records. These aggregated data sets can then be matched with other first-party data in order to gain more meaningful insights. This matching doesn't have to just apply to a situation with two parties. It can extend to situations such as multi-party matching, where there are more than two parties involved. And it can also be applicable to a scenario where there are two different departments within the same business that need to keep their data private from one another. And some of the main benefits of data clean rooms include having access to a larger pool of data and being able to provide more in-depth analysis. Data clean rooms also protect data privacy and security in a way that adheres with the current regulations and laws as well. So a common example of an implementation of data clean rooms can be between an advertiser and a brand, powered by Snowflake's distributed data clean rooms. Here, like we can see on the right-hand side of the screen, we have a popular brand. This brand might have a data set containing attributes about their customers and the associated purchases that they've made. This brand might want to reach out and attract new customers that have the same kind of attributes as their existing customers. In order to do this, the brand can match their data with an advertiser's first-party data. By doing this, they can gain additional information, such as matching these already existing attributes with other common characteristics in order to drive upsell opportunities. These secured joins are governed by pre-made query templates and requests in order to make sure that the data sets provided by the advertiser and the brand are kept private from each other. Another example of clean room implementations are Snowflake secured user-defined functions. In regular SQL UDFs, the internal optimizers sometimes reorder the filters so that they are executed as early as possible in order to reduce the workload for the remaining query. In these cases, it's more efficient because it carries out quicker. However, it might cause hidden data to be indirectly exposed in subsequent queries, which can be dangerous. To protect against this, Snowflake secured user-defined functions don't use these types of optimizers and also prevent certain types of filters from being executed earlier. In Snowflake, this is simply enabled by defining the user-defined function as secured. The second pillar of data privacy engineering that we'll be covering is homomorphic encryption. This is when mathematical algorithms and operations can be applied to encrypted data. This ability removes privacy barriers so that data sharing is enabled, and also makes sure that if the data security was compromised, it would still not be as dangerous because it's in ciphertext form. There are two main types of homomorphic encryption, so that's fully encrypted and partially encrypted. Full encryption refers to a scenario when any function can be performed an unlimited amount of times on the data without requiring any decryption. On the other hand, partially encrypted methods allow certain types of functions to be performed an unlimited amount of times. However, other types of functions would first need to be decrypted before those operations can be carried out. Whether a business would use fully or partially encrypted methods would depend on their use case and the sensitivity of the data. To show how homomorphic encryption works, let's take a look at a simple example involving healthcare data. Let's say that this hospital has provided some raw values, as we can see, 5 and 10. Just by summing these two values together, we get 15. But it's not safe to provide these values to an authorized user, whether it's in an individual raw value form or it's in an aggregated form. So in order to make it a bit more safe, we need to first encrypt the data. So we can do that using homomorphic encryption and applying some mathematical algorithms to this data. So here we have a very simple scenario where we're just doubling the values. So 5 becomes 10 and 10 becomes 20. And we can see the total of that is 30. So what this shows is that the relationship between the individual values and the aggregated amounts remain the same whether it's in the decrypted format or the encrypted format. And now that it's encrypted, it's a bit more safe to pass on to that authorized user. So there are several examples of homomorphic encryption libraries that are available, and these include Microsoft's Seal and IBM's HeLib. Microsoft Seal is an open source library which empowers software engineers to build end-to-end data encryption storage and computation services. And this supports both symmetric and asymmetric encryption. On the other hand, IBM's HeLib is another open source library which has proven that AI algorithms could be run on encrypted data. And the main business proposition of HeLib is that it allows users to perform business logic on both decrypted and encrypted data. Both HeLib and Seal employ something called the BGV and CKKS schemes, which enable real exact value and approximated arithmetic to be performed on encrypted data. So now third, we'll move on to differential privacy. Differential privacy refers to when there's a system of sharing information about the patterns of groups of a data set, whilst withholding information about individuals. When differential privacy is used, statistical noise is added to the data, as opposed to providing the real values. The amount of noise added ensures that the aggregated statistics are not too different from the actual values. So this is a really good way and a really measurable way of balancing privacy needs with data accuracy. When implementing differential privacy, it's really important to consider the privacy budgets of the individuals within the data set, as every time a differential privacy calculation is used, it uses up a part of the privacy budget. And this is really important to account for because once the privacy budget has been used up, an error is raised and further work can't be done. So to explain differential privacy, let's again look at a really simple example. So here on the screen, we can see two data sets, the green one at the top and the blue one at the bottom. Looking a bit more closely at the data sets, we can see that the data sets differ just by one record. So Natalie, who's age 24 in the green data set, has been removed in the blue data set. So this record has been removed because a randomization algorithm, denoted as M, has been introduced. And the purpose of this randomization algorithm is to make sure that people looking at the data set can't identify information about individuals. This randomization algorithm also causes the probability distribution to shift. So we can see at the top and the bottom, comparing the two graphs, you can see that the bottom probability distribution is a little bit more shifted to the right compared to the top. So now that we have these two probability distributions, we can use something called the Renyi divergence formula to calculate the difference between these two. And if this divergence is less than a small amount, then we can consider these two data sets to be differentially private. So this is just one example of differential privacy. Another example might be if we wanted to change the age of each of the people in the green data set by 1 or 2. That would be another example of how we can add a little bit of noise just to change the data set. Some examples of available differential privacy libraries include Google's Pipeline DP, diffprivlib, and Smart Noise Core in collaboration with OpenDP. Pipeline DP is an open source framework which allows users to enable differential privacy aggregations on large data sets using batch processing systems such as Spark. So the main value proposition of Pipeline DP is that the APIs are familiar to Spark developers, so it's a bit easier to use. And also, it can be used in conjunction with something called the DP Utility Analysis Toolkit, which is a really great tool in order to visualize and quantify privacy budgets. On the other hand, diffprivlib is a more general purpose library, so that's better used for experimentation and trying to understand the impacts of differential privacy. But it can also enable users to create their own differential privacy applications. Finally, Smart Noise Core, in collaboration with OpenDP, aims to connect theoretical differential privacy applications with real-world deployments in order to make differential privacy more accessible. So now on to the last pillar that we'll be talking about, AI fairness and bias. With the dramatic rise in the use of machine learning and AI models, it is becoming increasingly important that businesses adhere with ethical AI frameworks and guidelines. And this is really important to make sure that bias is minimized and fair outcomes are achieved for all. There are laws across several countries which define attributes such as age, gender, class, color, religion, age, familial status as protected classes. This means that if an AI model uses one of these attributes without justifiable cause, they may be breaking the law. In addition to the legal ramifications, it's also important to consider that bias can appear in both conscious and unconscious forms. So a common example of this is using biased historical data in order to train machine learning models. So keeping all of this in mind, it's really important to make sure that bias is minimized at all stages, whether it be the data that we use, the models that we use, or the review processes that we implement. So to expand on the idea of how historical data can create a vicious cycle of algorithmic bias, let's take the example of a biased data set. Let's say that this data set is either gender biased or only has a small sample size of females within the data set. This data set can then be used to train the machine learning model. And as this acts as the training data for the model then learns to behave similarly to the data that it's received. Because of this, it creates biased predictions of the misrepresented class, which in this case, of the protected class, which in this case would be females. And as these bias predictions are the output of these models, these would form the output data sets. Now let's say that these output data sets were fed as input data sets into subsequent models. This would perpetuate the bias even further. So this example is a really great way of showing how bias at just one stage of the process can carry on all the way forward. And therefore, it's really important to evaluate it at all stages and make sure that there are measures at all stages to protect against this. So finally, there's some remedies for this, and these include some AI fairness libraries. AI fairness libraries are tools that provide reporting metrics, mitigation techniques, and reporting tools in order to help data engineers to detect and minimize bias. So a key example of this is the AI Fairness 360 library by IBM. This package comprises of over 75 different fairness metrics, which you can use to test the bias of your data sets and your models. It also comes with over 10 different bias mitigation techniques, including the disparate impact remover and reweighing algorithms. Other examples of prominent AI fairness libraries include things such as scikit-learn-fair, FairLearn, and FairSight, which have similar offerings but also have some additional features. For example, FairSight enables you to create visual analytics, which really helps to improve the visibility and the transparency if there's bias in the system. So overall, to summarize what we've talked about, the four main pillars of privacy data engineering that we've covered today: data clean rooms, homomorphic encryption, differential privacy, and AI fairness and bias. So I'll now hand it back to Lalit to talk about how this fits into the wider data engineering context and for some other closing remarks.
Thanks a lot, Ashika. So we looked at the four pillars of data privacy, right, and how they are important for a privacy data engineer in their day-to-day work. But I think it's also important to make these techniques, or why we are doing them, understandable to the stakeholders, right? Because they are essentially paying for it. And it's a hard balance, because a lot of the things that we looked at, they had mathematical context. Some things are kind of obfuscated, not clear to the business. So the way we kind of approached it is make it understandable to different stakeholders, get your support system in the organization working through on this, and the support system could be your compliance teams, your legal teams, risk teams, privacy teams. Those are the ones who are closer to these areas and would be able to help make the business stakeholders understand this. So kind of collaborating more with them in identifying the right stakeholders. At the same time, sharing some real world examples, as an example, the way we looked at the re-identification attack due to credit card transactions, right? That could give a good context if you want to start these kind of conversations in your organizations. A tried and tested method showing the before privacy treatment and after privacy treatment, what are the changes in the data, like if you're applying certain rules, for example, changing age to age band or income to income band, giving those examples to the stakeholders to make them understand. Now putting it all together, we apply certain exploratory analysis, we understand the data, we apply engineering techniques, do the post-analysis, make the stakeholders understand what we've done, and then making that data available for AI systems to use to bring this whole cycle together. So that takes us to the end of the talk, but before closing, it'd be good to deep dive into what next we can expect in the privacy space. The techniques we talked about, they are complex and they are costly. They need a lot of compute. So in future, there might be further improvements in these techniques to run them in a more cost-effective way, or newer techniques that can be run in a cheaper, faster manner. Bringing user consent into the mix, right? If a user tells us that they don't want to be involved or they don't want their data to be used for analytical purposes, how do we ensure that we then go back and remove their data from different systems in an organization, right? And that's where consent-based tagging in the data would be useful. Then organizations have different frameworks, be it legal framework or be it a risk assessment framework, trying to figure out, giving every data set some sort of privacy score. Before treatment, the privacy score was lower, but after treatment, it's much higher and above a particular threshold that it becomes shareable. Self-service privacy, right, in an automated way, trying to find out if a particular column is a PI column, and then applying certain transformations on that column itself. And lastly, probably a bit of a left field option where people can actually feel, fine, my data is there with me, it's needed by advertisers, it's needed by brands, then why not monetize my own data, right? Get your data available to the organization, to different organizations, and get paid for it. So yeah, it might look a little futuristic, but I do believe there is a possibility of such things happening as well. So yeah, that takes us to the end of the talk. We are open for any questions, but if you don't have any questions now, our email IDs are there, and we can connect with you later as well. Thank you.
Yeah, what techniques can you feasibly use on streaming or real-time analytics data, or do you use any techniques on that?
Yeah, so all the processes that we talked about for now, they essentially are around a batch data ecosystem. They are slow-moving processes. From a real-time context, it's ideally around using some sort of a Lambda architecture where you have real-time data coming in, but then you have some historical data which is privacy treated. So for example, if you want to, let's say, do fraud detection, you want to see some historical data. So you're not applying these techniques on the real-time data that's coming in, but using your historical data, which is kind of privacy treated. So that's where probably the context with streaming lies.
I think you talked, Lalit, a lot about data encryption and data encryption at rest, and also you brought in all of these third-party libraries. How are you profiling those third-party libraries so that we know that the data is doing what those third-party libraries are saying they're doing, which is encrypted at rest? But how are you profiling those libraries to check them?
Yeah, so So there are two ways of doing that, the way we approached it. So one is all these libraries provide their testing frameworks as well, right? So like if you have worked with scikit-learn, they have their test framework. The AI Fairness 360 that Ashika talked about has its testing framework. So you can generate metrics after doing some privacy treatment. How much was the bias, before the treatment, and how much was the bias after that. So they do come with their own test suites. And then, in some cases, we ended up writing our own tests as well to essentially validate the outcome. So the risk assessment framework that I talked about, that essentially looks at, what was the privacy score, beforehand, and after treatment, what are the privacy scores? And that's essentially driven by how easy it is to kind of join that data back to some other data sets that we have. So yes, we are leveraging testing suites within the tools, as well as some of the test suites that we built ourselves. Sorry,
I'll repeat the question for the benefit of the microphone. And those tests you're running yourself, they're what's checking the data is actually encrypted as it should be in the call stack and in certain places in the DB engine and DB storage as it should be, and all those sort of really nooks and crannies.
Yeah. So tests around that encryption. If let's say it's a it's a SHA-256 that we are using, making sure that afterwards we have 256 characters in the resultant outcome. Those are some of the basic tests that are being performed. But encryption in at rest and encryption in motion, that different concept. This was more about using data which is already encrypted. So we are not decrypting. The concept of homomorphic encryption is you are not decrypting the data, right? You are using the encrypted data to essentially run some of the matching algorithms as I talked about, right? So if both parties encrypt data in the same way, they are, and exchange keys, they can then use the data in encrypted form.
I had a question on the, you mentioned a point around managing the balance between usability and privacy treating the data. Are there any guidelines or principles? How do you maintain that?
Yeah, that's a great question. The way we kind of approached that problem was essentially around trial and error based approach, right? So there are no framework as such right now, which we've used to enable that. But one of the things which Ashika called out was around the privacy budget, right? So with that budget, essentially, you can set a certain threshold on that budget, and the more you use the data, the budget gets down. So eventually, if you exhaust the budget, you end up, finishing up your usage of the data. So it's a fine balance when you treat data for usage, and it's essentially use case by use case. With as I mentioned, if your use case is purely recommendation engine, you can perhaps do a little lesser amount of privacy treatment, make it a bit more usable, right? So, and if your use case is more of a, let's say, fraud detection, you can do the other way around. So they are both inversely proportional, and it's driven by the use of the business and then the use case. Thank you.
Thank you, Lalit. Thank you, Ashika.